So the recording is on and the audio is on. So if you remember this is part 2 of the previous video. So if you're just finding this video, go look for part 1. We're talking about singular value decomposition and recommender systems. So I'm going to open up the Jupyter notebook, and I'm going to basically pick up where I left off on Monday. So I need to navigate to the script. So I'm going to share the screen. Okay. All right. So you should be seeing the screen now. So let's see, the script that we were working on was we have the data and recommender. Right. So if I go to this folder, we're using movies.csv and ratings.csv. Those are the 2 files. And then our Jupyter notebook is recommender system in class. Okay, so I'm going to click on this one. All right, and here we are. So this is the code. So you should be seeing the code now. So I'm going to kind of quickly go over it again, just to kind of remind us of where we are in this. And then after that, we're going to finish it up and talk a little bit. I'll do an example of a recommender system and how that works on the whiteboard. And then after that, basically it's working on the homework. So this, the way that, I already explained a lot of things about the relationship between singular value decomposition and recommender systems. So again, go back to that part 1. So, what I've done with this topic is I kind of started with the code first, and then I'm going to go back to the theory. So my plan is to cover the theory of singular value decomposition on Monday, actually. So in that video, I'll cover singular value decomposition. And then if you remember, we had talked about how singular value decomposition is unsupervised. And in this class, we're using it for both compression of features and also for recommender systems. So all of that is in the previous video, that discussion. Basically on Monday, I will cover the theory and the background of singular value decomposition, and then I'll get into the compression part and feature dimensionality reduction. So it's similar to anyone that's familiar with PCA, principal component analysis, is a similar idea. But I will go over, as I said, the theory of singular value decomposition and also compression on Monday, that part of the code. This week, we're only focused on recommender systems and singular value decomposition. So I've given some intuitions of singular value decomposition so far, but I haven't really gone into the theory yet. So instead, we're just going to finish up the code today. And I will do an example of the intuition, basically, that should be pretty good and should give you better ideas as in relation to the homework assignment. So remember that the homework assignment will be to find another data set. So this data set is about movie reviews, movie ratings. You have users in movies. So I'll do the example on this. But for the homework, and I'll write this out on Brightspace, students have to get other data sets instead of movies and basically make recommendations. So maybe you get a data set on supermarket products, or you get a data set of books, or you get a data set or anything, right? So that we can sort of make recommendations. So this is a homework assignment that you guys will have to demo so that I can see in your system, okay, you can in fact make some recommendations. All right, so that out of the way, then that's kind of the plan for this week. So today, definitely, I would like to finish recommender systems, the code, and I think we're pretty close to finishing it. I covered a lot of it on Monday, so we should be able to wrap it up. All right, so I'll do a quick review. Of it. And then just loading up my files. Okay. So let's see, I need, okay. All right, so here, okay, so now we can go ahead and, just, I'll go over the code again just to quickly review. So basically we started out with the two libraries, NumPy and Pandas. Okay, so we have those two libraries. I'm using the movie lens dataset from grouplens.org. There's a lot of data there. The one used here has 100,000 basically ratings or records or however you want to see it. And also the statistics is that it has 620 users and 9,724 movies. Okay. One of the problems that the data has is that the IDs for users do go from 1 to 620. So I don't think there's any problem there. But the IDs for movies go from 1 to 170,000. And it skips a lot of numbers, obviously. So there aren't 170,000 movies. There are only 9,724. So there's a couple of ways that this could have been handled. Given that I'm anticipating your homework assignment, I did something where I do a mapping of IDs, which are calling ref IDs, and then to the real ID. So that way I have ref IDs, which are from 1 to 9,724, and those are mapped to the real IDs, which go from 1 to 170,000. And that's just so that when you guys do your homework, it becomes a little bit easier to find the products. All right, so the first thing we did is we went over, we loaded the data, the ratings data. We looked at the unique values of users and movies. We printed out the length. Those values would match 620 and 9,724. We also looked at the data with the data head there, and you can see the data actually here. So we have here this is the ratings file, and we have for a user every user can rate several movies, right? So they don't rate all the movies. So there will be some movies and user combinations that are 0 or not a number, right? So we have to handle those as well. But otherwise, this is the format of the file. So we have a user, let's say user 1, John Smith, and they rated movie 1, The Matrix. Okay, and then they give it a rating of 4, so that means they kind of like that type of movie. Then they rate movie 47, and they even like that one even more, right? So it might be some other movie that they're more into. So remember that all we have in the data is the users, the user IDs. We don't have their names, but we have the user IDs. And then we have the movies themselves, like the names, The Matrix, So these movies do have a genre. The genre is in the movies file, like science fiction, comedy. But what I want you to understand is that is data that we are not using in this, right? And this will become more obvious in the example that I'll do after the code. So the movies, we're not using the fact that, oh, this is a sci-fi movie, this is a comedy, this is romance, this is action, right? Instead, we are going to try to use singular value decomposition, the theoretical framework of it, to kind of statistically figure out those things, okay? So that's the idea. So we use singular value decomposition, which, like I said, I've already given it. I'll give more of it today, and then we'll go over the theoretical, the more formal theoretical framework of SVD on Monday. So just making sure I'm recording. Okay, so so now we talked a little bit about that, so I went over that. Then after that, that was really just to visualize the data. So maybe I should write on here. This is just This is just to visualize data, okay? It's really not for anything else. And then after that, this is the actual data we use. I can write here, this is the actual data we will use. And really, for singular value decomposition, we only need to use rating CSV. So SVD uses ratings only. The other file, the movies file, is really just there so that we can do lookups once we apply singular value decomposition to the data ratings frame, pandas frame. Then we're going to get some results, but it's going to be a whole bunch of numbers, IDs, etc. And we need to do lookups of those IDs to match to the actual movies so that we can print out something that is readable. Okay, so that will be the next step. So here we have, so that's the actual data files. Okay, also remember I gave you this code. I'm not using it right now, but I just showed you that this is code that you can use to, break the frame into train and test. In case you think you might need that, that's what this is for, and I explained it in the previous lecture. All right, so now that we're here, right, the first thing that we need to do, as I described in the previous video, is that we need a matrix. In this type of analysis, singular value decomposition, because it's unsupervised, we don't need, like in supervised learning where we needed to have X and Y, right? So in supervised learning, we needed X and Y, so the X matrix and the Y vector. Here for singular value decomposition, we don't need this one. We only need the X data. And so our X data is going to be a matrix of, let's say, users to movies. Okay, so it's going to be a matrix of users to movies. So that means it's going to be a matrix of 620 to, let's say, 9,724. I think that's what it is. Okay, so that's the matrix that we need to create. Okay, so in the code, we can go back to the code, and you can see here we creating the ratings or X matrix, which is rows as movies. So it's actually rows as movies and columns as users. All right, so you can see there, we're going to call it ratings underscore mat, and it's going to be a numpy of zeros of shape 9,724 by 610 of some data type. So right now it's uint8, but of course we can always change that to some other data type. You can print the shape of it, and you can see the shape down here. So it's 9,724 by 610. Okay, so that's pretty much done. Once we've created the matrix, then we can proceed. We want to proceed to get the values of the matrix, right? So we want to get the ratings. So to get the ratings from the ratings, we need to get them from the data ratings frame. Okay, so that's going to be data ratings, and then the column rating, and then from it we get all the values, and we get ratings array. When we do a length, if we do a length of ratings array, we would get a total of 100,000 examples. Okay, we do that for all the other ones. So we do that for movie, because the data ratings matrix, if we look at it, right, has user ID, movie ID, and the ratings themselves. So we can just basically get all this data by column. So in this code here, I'm just grabbing each column. So I grab this column, then I grab this column, then I grab this column. And you can see what I'm doing is I get all the ratings. So there's 100,000 of them. I get all the movie IDs, which are repeated, right? So they're repeated. I get user IDs, all of them as well, and 111, all of these. But in total, they match, right? So there's 100,000 entries. So there's this is one full entry, then this is one full entry. So every time they're aligned, and I'm grabbing the correct data. Once I have that, I can do the length of it. you know, I did it for users. There's 100,836 in there. So that's good. Now that I have the data comes the part where I kind of left off on Monday. So on Monday, I was saying that I wanted to create these dictionaries that basically just do a mapping of the real to the ref. And that's really because the movies themselves are an issue. So in the movie IDs that we have in the data set, the movie IDs go from 1 to, I think, 170,000 something. I can't remember. So that means that, you know, this is the Matrix, you know, and this is, you know, Out of Africa, you know, and then Star Wars, I don't know, 500 somewhere in there. Star Wars, right? So we have all of these movies in there, but there's a lot of missing things. You know, we might go from 168,000 ID to 170,000 with nothing in between. So in the end, we really end up with just one, you know, from 1 to 9,724 IDs. So what I want to do is I do a mapping. I create a dictionary, right? And, you know, the mapping basically will do this. So this might be 8,000, I don't know, some number, right? And that way, I will use these numbers to create the matrix, the dimensionality, because I don't want to, I could have also done a matrix that is 620 by 620 by 170,000, but that would have been too big, and then, you know, it's gonna be too much on the RAM of my, on the RAM of the computer, basically. So by doing this one, this version here, I'm saving in RAM, and that, you know, the program will be able to process. So that's really the idea. And so that's what I'm doing. I'm just creating this mapping. Okay, so that's the next part of the code, which will be very useful for your homework. Okay, so it'll make your lives a lot easier, because regardless of how you get your IDs, you can just do a simple mapping, and that should be enough. So, you know, basically there's two segments of code. This one is for the movies, and then this one is for the users. Okay, so we can take a look at the code, you know, just really quick. We can see here that we have, so let me just save it. We have movies, uniques. So I create two dictionaries, you know, a dictionary, which is called a reverse, you know, a forward and a reverse dictionary. So one it's the same information. It's just that in one dictionary, the ID is the ref. Okay, so the new ID, and the value of it is the key and the values, right? So the key, so if you look over here, you have a dictionary, usually, and it's got something like this. So this is the value, and then this is the key. Okay, so in this scenario, ref is the key, and then the value is going to be the actual ID of the movie, right? So this would be 9,724. This would be 170,000. In the other dictionary, I just do the reverse, right? So the reverse would be that here the real is the key and the ref is the value. So it would be dictionary. So this would be, I guess I should say, 9,724. This would be 170,000. Oops. Oh. Yeah, so this one would be 170,000 or whatever it is. Right? And this one over here is the opposite. And the reason why I do this, dictionaries in Python or hash tables are very efficient, but by doing this reverse dictionary, I can just speed up my processing. Okay, so I have, you know, I can just do lookups really fast. So here the ID, the key is actually the real movie ID, and then the value is the 9724. Right? So they're just inverted, and that just saves me time when I do the lookups. So I do this for both things, for both the movies and the users. So here you can see once I have my dictionaries created, I'm going to take movie IDs array, which is this one up here, which had 100,000 or so. movie IDs, right? But they're repeated. So I need to get the unique versions of them. So I just do numpy unique. And that gives me an array of unique movies, which is going to be 9,724. But it's going to be the IDs. So there's going to be like, 170,000 will be in here, right? So those values are there, but only not repeated, just unique. After that, I just go through the array movie uniques, and I'm going to enumerate. So I'm going to do for IDX res and enumerate movies unique. This just, every time I grab a real ID, a real movie ID, I can also get the corresponding index in that array and the value of it. And so that way I have, okay, if it's 1, it's going to be whatever the ID is, probably 1. And then for the last one, it would be IDX 9,724 with a real value of 170,000. Once I have this, I just proceed to populate the dictionary. So I think this should be pretty obvious. I invert the values. So ref to real and then real to ref. Okay, and I do this, and now my dictionary is ready. And then I don't have to explain the next one because it's the exact same thing. I just do this one for the users. So for the user IDs array, right, I get the uniques and then populate the 2 dictionaries. With this in tow, I have now my dictionary, right? So we can go ahead and run the dictionary here just to print it out. So I'm going to hit run. And you can see here the dictionary is created. It's pretty big. And then, but you can see the last one is, because it starts at 0, so the last one is 9,723, which maps actually not to 170,000, but 193,609. Okay, so I don't know why I remembered 170, but it's actually, it goes as far as 193,609. This is the ref ID. This is the real movie ID from the data set. Okay, so once I've created that, that's great. I'm going to go ahead and clear this from the kernel. Okay, and I'm going to remove this comment. And now that I've created the dictionaries, we are ready to continue. So I kind of wanted to just repeat all of that really quickly, so I didn't just start from everywhere. However, if I miss some detail, it might be in the part 1 of this series, singular value decomposition and recommender. So take a look at that. All right, so now that we've done the dictionary, we are ready to continue. And actually, we are very close to the end of the code. Because like I had said before, if I go back to the whiteboard here, like I had said before, the code is actually pretty simple. Now, singular value decomposition itself is not trivial, right? So it's a linear algebra technique. There's quite a bit that goes on there. I will cover some of that on Monday. All right, so Monday I'll cover the algorithm of SVD basically. Okay, so that I'll go over some of the intuition of singular value decomposition on Monday. But really, the code that I'm providing right now really just has an SVD function. So it's pretty easy. You give it X, and it's going to give you USV, which are 3 matrices. All right, and once I do this, after I finish this code and we go over the example, it should become pretty obvious how that works. But really, this code, this is just one line. This is done in one line of code. And so really, everything leading up to it is what I've been talking about, like just getting the data, the dictionaries. So usually, if you think of the machine learning pipeline, this is just data processing. That's all it is. Most of that code, is data processing, getting that X ready, as a final product, which becomes the input to the singular value decomposition. Then the next part of it is using the U, S, and V matrices to recommend. And this is the part that I will, that code I'm not going to provide. Instead, I'm just going to explain it between today and Monday, and then let you guys infer things from this, okay? But basically this, the code here should give us everything that we need. So really, as far as SVD, there's only one line code. So we can go back then to the Jupyter. Okay, and now that we have this Jupyter here, we can just proceed to the next part. So all that remains after we have created the two dictionaries is we can do what do we want to do? Oh, what's the next part? So currently, if we print our matrix, right? So if we print our initial ratings matrix, there's nothing in it. Okay, so we can go over here, do a print over a matrix. We haven't really we got the data in the dictionaries, we initialized it to all zeros, but we have not actually populated it. Right, so if we take a look at it, you can see the matrix here is still all zeros, right? But it needs to be a matrix of users to movies, or I think movies to users, right? Movies on, as the rows, users as the columns, and then we need to have, instead of zeros, we need to have the actual ratings. Okay, so that's the next step then. We know there's 100,000 values in the ratings array, right? We can print out also the ratings array if we'd like. So we can do, it's called ratings array. So that contains all the values that we need, right? So we need then print ratings array. So if we run that, we can see here, these here are the actual ratings. And we need to extract every single one of those ratings and populate them in here. Now we do know from looking at this, because we have the two columns, user IDs, movies IDs, ratings IDs, these are three matrices that we have. We have three matrices already set up, but we know that each row is a one single entry, right? So what this means is that row 1 here was user 1, movie 3, but movie 3 the ID, right? Not movie 3 not movie 3 like what corresponds in the matrix that we're going to create, movie 3 ID. So we're going to have to do the lookups when we populate this data. So for instance, whenever I say user 1, I need to do a lookup in the dictionary. That'll probably be 1. You can always just print that dictionary. It's not very big to take a look at it. But when we say movie 47, because the IDs go from 1 to 193, and that would be too big of a matrix, we're going to have to do a lookup on the dictionary for ID 47 to see that's the real ID. We want to get the ref, and the ref will probably be, let's say, 19. A much smaller number, but that will allow us to process a much smaller matrix instead of having to have a sparse matrix or a really large matrix. All right, so that's the next part. Then we need to iterate by index. So we know that each entry shares an index, right? So we know this is index 1 for all three arrays. This is index 4. So if we look at index 4 and user ID array and movie ID array and rating array, we'll get 1, 50, and 5, which are the values that we need. So with that information, we are well equipped to populate the ratings matrix. So we're going to go ahead here and perform that task. So now what we need to do is, basically, there's a lot of ways that you can do this. I'm just going to do a for loop. It's the most obvious. Obviously, for much bigger data, pandas, NumPy might be a better approach, but here this is actually fast enough, so we don't have to worry about it. So I'm just going to do for I in range. For I in range, a for loop, and what I need is the length of ratings array, right? So because there's 100,000 entries, so I need to get all of them. So ratings array, right? So this will allow me to iterate through all 100,000 of these, right? So there's 100,000 of these. And so, you know, I'll grab the first index and the second index and so on. So I'm going to go over here. So I've got the length, all right, length of ratings array for I in range. So it's going to be for I in range of basically 100,000. That just gives me the indices that I'm going to need. And then now I can proceed to populate the ratings matrix, right? That's what I need. So I want the ratings matrix, right? Which is, you know, this thing that we've initialized to all zeros, np.zeros. We are going to assign to it. So, but we need to provide, obviously, the indices, right? So that's where the tricky part comes, because we know what gets assigned to it. That's really easy. So we just need, from the ratings matrix, from the ratings array, right, which has the 100,000 ratings, we just need the value, right? So I'm going to say ratings array index, right? So it's just going to be I. So I've got that rating. But the thing is here, this is a two-dimensional matrix. So I need to provide movie and I need to provide user, right? So now I'm not going to provide the actual IDs, right? Because that would make it too big. Instead, I'm going to provide the ref. So I'm using this term ref. So I'm going to say ref M for the ID reference of movie. And then I'm going to say ref underscore U for the user reference. Okay. So then obviously I need to get those. And the way to get those is to get them from the dictionary. Okay. So I'm going to say ref underscore U, and I need to provide that value. And then ref underscore M, and I need to provide that value. So I've got both of these. So what is ref U? Okay. So ref U is the reference. I need to go to users, right? So one of the two dictionaries in users, right? One of these two. And I need the ref given the real ID, because I have real IDs in these matrices. In users, I have the real ones. So then, although they will match in users, I thought, you know, I did it for both because I don't know what your data will look like for your homework. So then I need to go to the dictionary users, uniques, dictionary underscore. And now I need to pick the one that I need. So I need, given the real, I need the ref, right? So given the real, I need the ref. So therefore, it's going to be real to ref. Okay, just like that. And so then I just need to provide in the index the real value. What's the real value going to be? It's going to be from user IDs array, right? From user IDs array, that index, because it's the same index that matches ratings array. So then in here, I'm just going to say users. So it's going to be users IDs, right? Let me just make sure I'm doing this right. Users IDs array. Array, and then of course the index is the trick, I. So it's the same index. But boom, that's it. You know, pretty simple. And then I repeat the same exercise for the movies. So again, I'm going to look for that dictionary. So it's called movies uniques. Movies uniques dictionary. Again, I need to think. I have the real value, right? And I need the ref, because this is the ref. So I'm going to say real ref. Then in square brackets, now I need to look for the real ID in the movies array. So it's going to be movie IDs. Did I say users? Oh, I think this should be user. Huh? Yeah, this is user, sorry. So then I look at the array. This is movie IDs array. Maybe I'm just going to copy it. Probably better. Movie IDs array. And I need given that index I. Same thing. Pretty straightforward. Oops. Too much. Okay. There. Just wanted to be aligned. So therefore, I have the data that I need here. Okay, I have my data. I'm able to get the refs, and now I can populate the matrix. Later, when you have an ID that you've identified in the array of interest, you will have to do the opposite. You'll have the ref, you'll have to go to the dictionary. I have this ref ID, I need to look up the real ID. And then once you have the real ID, you'll have the real user and the real movie. The users, we won't really need that much, although, well, that we'll see. But the movies, certainly, we want to get that right because, you know, that's what you're recommending, right? You know, imagine if you were recommending on your own site, obviously you'd probably have, instead of a movie name, you'd have like an ID, and then that ID is something that you can look up in your database, you know, like the SKU, right? Like the number of the product, and then that will give you URLs, prices, discounts, all kinds of things that you can bombard your customers with so that they'll buy your product. Remember, recommender systems at the end of the day are a real tool to make you more money. I mean, literally, right? You'd run this every night, update your database with new recommendations every night, and hopefully the difference would be that in a month, you know, without this, you would earn less than with this. So, because people, you know, consumers have a you know, behavior, and sometimes they're a little bit impulsive. Sometimes they want a product, but they forget, and then you remind them. You know, you go to Strag Van Til, for instance, if you've ever gone to that supermarket, everywhere you look, there's a bottle of wine. So, you know, even though you probably went in there for cheese, you see it so much that you're going to probably leave there with, you know, a bottle of wine or something else, right? Or the classic example of parents who go to buy diapers and then they put the beer next to the diapers, you know, all kinds of things like that. So those are the same ideas. But anyway, at this point, hopefully, we have our matrix, right? We have our matrix. So then we can try to print it again, right? So let's see if now we print it again, we have data in it. Oops. Okay, so that's it. I mean, this code, it's not really that complex, but it creates your X matrix. I thought about calling it X matrix, but you know, you guys understand. So you can use your own name if you'd like. You can call it X matrix. So now let's go ahead and run it again, and let's see what it looks like. So I'm just, you know, and we're almost done, by the way. This gives us the matrix, so now we can basically take that X matrix and run it through our singular value decomposition function. So let's run this code. And you can see now that there's a lot of zeros. So look at a couple of things. Look at this. You see that this one was all zeros, right? This one is not all zeros, but there's a lot of zeros. So it's not fully populated, and that's because, remember, that there's a lot of users that did not rate certain movies. Do you see that? So that's one of the key aspects there. But in theory, the matrix should be at this point because you're iterating, you know, through you know, the iteration is you grab this one, right? 1, 1, 4, 4. Well, there it is, 1, 1, 4, right? The very first one is 1, 1, 4. Then you do 1, 3, 4. All right, so 1, 3, 4 might be 1, 3, 4. Oh, it's this. it's this bottom one, right? This bottom one, because it's movies first. So it's actually movie 3, user 1. See, yeah, that's correct. And it just continues like that, but there might be a lot that are sparse. Now, for those of you, I always recommend with machine learning, I feel this is correct, but in machine learning, you always want to super double check. So what you might want to do is print out various parts of the matrix just to make sure that all the data is there. Okay, so definitely I always recommend my students, just go ahead and take a quick look, make sure that there wasn't an error, but in theory, this should work. Okay, this should work, and all your data should be there. You can always look at the bottom of this file, right, and try to find, okay, what was the last entry in it? So like if we went to, the matrix is small enough, so we can go to the GitHub, right, and then just go anywhere there. Right, so recommender, so you guys, you should be seeing. So we can go here, the data is here, and then rating CSV, view raw, sometimes it opens, oh, there it is. So then you can go all the way to the bottom and you can see that movie 178,000 does have a rating for user 610. Okay, so which would be the last entry. So you need to look up that value to see if it's existent there, okay? But that's certainly something that I leave to you guys. I believe the code works, but at the same time, just double check, right? That I didn't leave any errors. Later on, I'll take a look at it again. But I feel there's no reason why there should be an error, unless you guys can see something wrong. All right, so at this point then, I've populated the ratings matrix, right? We have visual confirmation here. We can also always do another trick, which is slicing. I can do, let's say I want to slice all rows, all movies, but only user, what is the last one? 609? 609, right? So let's do that one. If I run it, this is that vector, correct? That vector shows me that there's a rating for 5. We can also look up a specific one. So I closed it already. But I guess I want to just be paranoid. So let's say I'm going to look up one of these. So if I go to ratings, CSV, click on raw, I'm going to go to the very end. So I want to find that last entry. So this should be 609 and 9,000. No, that wouldn't be 9,000. That's the problem. That would be, but I can always look up this ID, right? And get this. Okay, so I know what I'm going to do. I'm going to grab this. So that I need to get a 3. So this would confirm. I'm just picking one. So I'm going to go to the code. Okay, I go to the code here. I'm going to use the dictionary, right? So from ratings matrix, I'm going to use my dictionary to find this entry. And it should return 3. So I need to give it the ref ID. So I need from users, uniques dictionary, I need real to ref. Okay, so I grab that. I'm going to plug it in here. I need to give it the appropriate one. Oh, this should be for users. And then for movies, I'm going to do the same. I need the real to ref for movies. So movies, or I think it's real to ref. Yeah, real to ref is what I need. Right, that's what I've been using. Real to ref. I'm going to plug that in there. Real to ref. Okay, and again, so I would need to give it then. This ID is the real movie ID. So real movies, right? And that'll give me the ref. And 610 would be the real user. And it'll give me the ref. Okay, in theory at least. So let's make sure I don't have any errors. Have that. Okay, so that should give me a 3 if I did everything correct. There it is. See the 3, guys? That tells me that I populated the entire matrix correctly. Does this make sense? Are there any questions about that?
No questions. Makes sense.
All right, this is just, let's put this under, something that you should always do in machine learning. Let's call it sanity check, right? So sanity check is just, you want to make these little, you write your code and you think it's correct, but you just want to double check, make sure. All right, so now that that's done, we did this example, we can just comment it out. We don't need it anymore. We're certain that it works. But I have my matrix populated. So now let's proceed, and we are almost done, right? So now the next step is, all right, so now the next step is to really perform the processing. So we did populated the matrix, we got that. And now, so the function for singular value, so this would now be the function for singular value decomposition. So the function for singular value decomposition, we're going to use from NumPy, right? So from NumPy, np dot, and NumPy has a module called linear algebra. So as you guys know, I mentioned that this is a technique from math, from applied math called from the area of linear algebra. So NumPy has this area, linear algebra, lin ALG, and within that we have a function called SVD. And then basically, for now, that's really as far as we need to get. We could do, let's say, we're going to do some additional processing to this, but let's just say right now, in this step, I'm going to take ratings mat, right? And I'm going to just simplify it to like A, just to make it a little bit shorter. And then that way we just plug in here A. Remember, when I do the example, I said that the singular value decomposition provides, it takes the one matrix and breaks it up into 3 individual ones, which will be U, comma, S, comma, V. These are just some names. That's just traditionally what the names are. Again, once I do more of the theory on Monday and I do a little bit more of the example today, the motivation for it, you'll hopefully get, start to get a better feel. But this is, all this work that you've done is for this. Okay, for your homework assignment, after you do all of this and run all of that, this is the thing that you want. Because that's the thing that you're going to now dive into, all those matrices, to try to figure out, okay, what movie do I recommend? The recommendation, well, the information is here, okay? And now you just have to build the rest of this to make the recommendations themselves, okay? And like I said, this part I'm gonna leave to you guys, but I will provide an example on the whiteboard, and then therefore you'll have to do a little bit of coding to get the relevant data from here to make recommendations. All right, so once we have this, let's just do a couple of things. You can always, of course, print you can print, you know, the matrices. I encourage you to do that. So print you know, print them like that. But more importantly, you know, print the shapes, right? So printing the shapes is pretty useful all the time. So we can do u dot shape and print we're gonna print s dot shape, and we're gonna print v dot shape. Okay, so we've got those two there, and that gives us the results, you know, that we might need. So let's actually enable that one. I'm not going to print all of them, but you know, I recommend that you do that. All right, so now that we have this, there's a few additional steps that are recommended between here populating the matrix and actually running singular value decomposition. But at this point, we really just want to see what happens. So let me go ahead and run it. All right, and there you can see. Do you guys see that? We printed out our two matrices, right? U, V, and S. So we can also do like, let's try, this would be U, comma, run that again. Right, so it gives us a little bit of information there. I'm going to do S. And this is why, because you know, you might have questions, but what is, you know, why does it have all those values? Why does it have all those dimensions, etc.? So that's why the theory for this is actually a little bit important. So we will take a look at it. But now at least you know, instead of, I like to do code first and then theory second, because that way you have questions, right? You're not just listening to some theory and you don't know where I'm going with it. You know where I'm going with it now, and so you'll be more keen to figure things out. So this is calculate, you know, SVD, singular value decomposition. Okay, so you know, now we run this. Clear them. And I'm going to run it. And there it is, right? So we have, look at the dimensions, right? For the U, it's in relation to the movies. Do you see how the original matrix, ratings matrix, was what? 9,724 by 610, correct? Do you guys see that? So look at what happened here. And this is very important because this goes into the foundational theory of SVD, right? So you should be seeing the whiteboard now. And if you think about it, remind me, so the movies go first, right? So it's the X matrix looks like 9,724 by 610. Right? That's the input. But after applying singular value decomposition, you get U S and V. Do you see that? And really what you're getting is, if you look at the previous example, this one is 9,724 by 9,724. This one is 610 by 610. And this one is only 610, which basically means it's kind of like a vector. Usually it's like a diagonal where everything else is zero. So really it only gives you, you know, some values like that. 610. So if we look at the code output, we see something very important. So it's 9,724 The other one is 610, and then this one is 610. Okay? So that's really something important, because it's saying, well, now if we go back to the whiteboard, it's saying something quite important. It's saying, well, this is in relation to movies. So this is something all about movies, all about movies. This one is 610, so obviously all about users. But it is a type of grouping. It is a type of grouping situation, right? Where here, you know, these are movies. But what are these then? What are these 9, 7, 24? Well, they're just called principal components. That's all they're called. Or sometimes, because it's singular value decomposition, they're called singular components. So this column, all the way to 9,724, those columns are just singular components. What do they mean? Who knows? But intuitively, for movies, it's possible, because movies, users will have a tendency to rate movies based on the genre that they like more than anything else, right? So I'm sure you guys love like Marvel movies, right? So what are Marvel movies? They're like fantasy superhero type of movies. You might rate all the movies, X-Men, you know, Wolverine, Captain America, you know, Thor, all those superheroes, right? You know, Iron Man, all of them. You might even also the DC comics, right? So you might say Batman, and you might say, you know, Christopher Nolan's movies. You know, a lot of that gets grouped in a category. So what might happen is that all those movies that are, you know, that type of superhero movie have a tendency to appear with high numbers in this column, whereas in other columns they'll have really low values. So it's like saying, you know what, for this column over here, it just so happens that the only movies that have really high values are the superhero type movies. Everything else had low values. So then what would you conclude about this column? What did the singular value decomposition approach, what did it infer for this column? What would you conclude?
It's comparing the likeliness of the movies to that singular movie.
So that's singular genre, yes. So it's like it detected a genre of superhero-y, heroiness. Do you see that?
So you're saying the top row is genres?
What top row? There's only
Well, the columns. I'm sorry, the columns.
yeah, the top rows are movies, and these are only called. All I'm saying is they're called singular values, right? Single components, those columns. But it turns out that, as I said, for the superhero movies, the values in this column will be could be really high, you know, like 0.8, 0.9. But then you get a movie like a comedy, right? I don't know, some comedy, and that gets a 0.20. You know, some other comedy, like a Will Ferrell movie, you know, 0.1. In this category, it grouped only the superhero movies. Now, the Will Ferrell movie might be over here, 0.7. So it's not necessary. That's actually a good example, because it's not just necessarily genres. It could just be that Will Ferrell becomes its own column. Do you see that? And so singular value decomposition does not, you don't tell it. You don't tell it, hey, singular value decomposition, find Will Ferrell movies. Or no, you give it the data, movies and users, based on the ratings of your users, right? Obviously, if you have only like a young group of people rating movies versus Gen Xers or whatever, you know, there might be some differences there. Do you guys see that?
Yeah.
But at the end of the day, it'll discover some things. Like it'll discover either It could discover something like superhero, very general, or it could just discover that Will Ferrell, it just so happens that audience loved Will Ferrell, and so Will Ferrell becomes its own, you know, he's not a genre, right? He's a certain style of comedy. There could be other comedy columns as well, but he just gets his own. Make sense?
It's making sense.
Do you have any further questions?
No.
But that's what I'm saying. So in this analysis, notice that we only gave it this and nothing else. And our goal is to get some insight, because the importance about this is, well, let's stick with the idea of we have Will Ferrell movies and we have comics, right? If we now on the other end, we have users, right? Do you see we have users? And here what we can do is the same thing. We have these columns, right? And they're inverted, but you know, we have these columns now. So the columns represent also groupings. So now you might have a whole bunch of users. And again, those users have really high for sci-fi. What does that mean? They like sci-fi, right?
Yeah, I was just thinking, but wouldn't the 610 by 16 represent the likeliness a user is compatible to another user?
Right, but isn't that the same thing? Because you don't just,
Oh, I see what you're saying. So the one column, well, the one row would be saying sci-fi and saying that all these users like sci-fi.
that's right, that's right.
Okay.
Make sense?
Yeah.
That's really important, actually. Because what you want to do, remember, is if you Josh, like, you know, sci-fi, right? And I also like sci-fi, we would be sort of in the same column. You see that?
No, yeah, that makes sense.
And now you and I are in the same column. I can, because of that relationship, or even better, we're in the Will Ferrell category, right? Somehow. And so now you can say, well, the Will Ferrell category doesn't just include Will Ferrell movies. There could be another one, you know, I don't know, another comedian that's somebody from Saturday Night Live maybe, they're similar to Will Ferrell. They also get thrown in that category. And maybe you have seen it, you rated it, but I've never seen it. You see? And then, but I like it, so the next day that movie gets shown to me and I'm like, okay, I want to see it. You see the point there?
Yeah, no, that makes sense.
All right, so this is what you guys will have to do. You will have to dig into the USNV to make recommendations, okay? That's why this homework assignment is a little bit more advanced in the sense you will demo and then you will show me, okay, Professor Calix, I picked products in a supermarket. I'll rate something. You'll add the entry in there, and then you'll make some recommendations, to prove. I mean, that's the whole point of this, right? And then I'll say, no, I still don't want to buy that product, or maybe I would buy it. Play with your classmates, your friends, but that's the idea. And that's the part that I'm going to leave incomplete in the code, okay? That's the part that I'm going to leave incomplete in the code, but I will do an example of this. Now, this is just kind of like the big picture because that's what the code gave us, but I do still want to go and do an example by hand on the whiteboard. All right. Before I continue, are there any additional questions? No? All right. Doesn't sound like you guys have any more questions. So let's see. Now, another thing that is sometimes that is recommended is to, obviously, I think I've said this so many times in the semester. What do I always say about your data in machine learning before you run it through an algorithm?
You should clean it.
After cleaning?
Process.
What's one thing that you could always do with your dimensions and new features. Scaling,
Oh,
right?
okay.
Scaling, right? So you always want to scale your data, right? So basically that means you take the values, whatever they are, and you subtract the mean from them, correct? And so that's something that you can do, always do that in a lot of ways. This is scaling or normalizing the data. So scaling or normalizing the data. Okay, so that's always something that you kind of want to do. So we're just that, but that's just literally like a pre-processing thing. It doesn't change the pipeline at this point. And you actually saw that we got results, right? We were able to see results because you can see them here. You see this? That's the matrices, right? So I only printed U, but we can actually print all of them. So print S, I forgot to do that, print S. You can also print V, and you have your data. These are the matrices that you'll have to process, of course. All right, and then I'm gonna run it. Oops. Oh, yeah, so I got rid of this. So I haven't normalized it. Okay, so now I'm gonna run it, and it's just doing its thing. So there you can see there's data in all of these. All right, and that's this is the first matrix, the U matrix. Then this is the, notice it's just a vector here, right? The vector. You see that? It's just a vector. And then this is the V, right? For the users. Now, did you notice something interesting in S? This is the S matrix. I just want you to notice something. Let's see if you guys are very, just look at the data. That's the matrix that I didn't talk about. Between U and S, there's another vector with size 610. Look at this data. What can you tell me about it?
Is that saying that movie ID 510 is the highest correlated one, or something like that, or 511?
Before you jump to that conclusion, just what do you see with the numbers? What's happening to the numbers?
Decreasing in value.
They're decreasing, right? It goes from 511 to 223 to 187, 163, all the way. So it's actually quite interesting. And I think you were right in what you said. You said, I think, that this correlates. There's 610, so that might correlate to the 610 columns, right? And it's saying, yes, the first one, the very first one that was given is the most important one. So that's like saying that, you know what, in the first one, I'm certain that's a superhero movies genre. You see that?
Yeah.
The next one, 223, I'm certain that's a Will Ferrell. But as you start going down to the last one, the last column, I have no idea what this is. I got some movies in there, but I couldn't really find like, some relationship or correlation. So I created these, but probably if you want to start somewhere, you want to start with the first column, like that first principal component. So that's like saying, to go back to this one, right? You want to say, okay, the most important ones are, let me change color here. The most important ones are these to the left, right? So it starts to decrease, like 610 or what? No, 5 something, right? 500, 233, and so on. Do you see that? So that's an additional very nice component, because it's telling you, by the way, you know which ones are more important. Where it was able to discuss a real thing about what users like, versus somewhere else where I didn't really find anything, but you told me to create 610 of these things, so here they are. because that's just the way singular value decomposition. It just creates these sort of square matrices. Make sense?
Yeah.
Yeah. We'll take a look at this, as I said, on the example, because this is a really important topic. So, you know, I think we'll wrap it up on Monday, really. But I still need to do, as I said, an example. All right, so anyway, that's sort of the intuition there. So it's always good to look at the data. I always like to run the code because this really helps us to understand the theory really well when we've looked at all the parameters. All right, so I just printed these. I'm going to go ahead and clear this out. All right, so I'm going to comment this out because it takes too much space. All right, that's a little bit better. Now, to normalize the data, there's a couple of ways that you could do this, just with a function, etc. Usually, you can also, because it's NumPy, you can just do the math, like take out the mean of something, right? So in this case, we want normalized matrix. So the normalized ratings matrix, right? So, which means we're going to take the original ratings matrix, right, that we have. We know that's 610 by whatever it is. And then now we're going to just subtract the means from these values, okay? So we're going to subtract the means. So I'm just going to run basically here minus, and then we're going to say numpy dot as array, okay? And we are going to calculate in here we're going to calculate the mean of this. So we're going to use numpy np.mean, and it's going to be the mean of ratings matrix. So later on, when we look at more NumPy examples, we will come back to this example just to kind of see the math of it. But for now, just kind of treat it as a black box. So we have, we specify the index, right, where we want to calculate the mean. So on the 0 index or on the 1 index, so the rows or the columns. And then we can do this, provide this within square brackets. So it creates a type of a list. And then we convert that list into a NumPy array. So we're going to calculate the values. Here we can always do the best way to do this would be to do a little example. So I would recommend, we'll do this, let's just say this. We'll do a little exercise later where we take, let's say, ratings matrix, right? Our 9, 7, 24 by 610. We're just going to make it like 4 by 4 or 4 by 6, okay? With some values in it, random values. And then we'll run this code, and that'll become, more intuitive what we did, so that we can understand the, the results of this. But for now, let me just finish the code here. So I'm going to say normalize ratings mat. We take the ratings matrix minus np.asArray. And then, as I said, this is a list. We're going to get the means of it. Then we'll take out of all of it the transpose of it, and that should give us, so basically what the logic is that we're taking the original values and we're subtracting the mean from it. All right, so we're going to say, for instance, here, subtract, normalize the matrix, subtract the mean. Okay, so if we test this now, let's just make sure it works. usually when you normalize your data, it's better result. Okay, so there's oh yeah, so it should be ratings underscore mat. Okay. Try it again. Right, there it is, right? So it still runs. And this, as I said, it's just really about normalizing the data. To get a better understanding of this, we just have to do an exercise of this. So when we go back to the NumPy examples, again, though, you can also just work this out on your own. You know, use what you've learned so far, create this matrix much smaller with some random data, and then kind of work out that we're just subtracting the mean from it. Right, the transpose is a term in linear algebra. It just means that you take a vector that is, let's say, something that is 6 by 10 by 3, right? And that will become 3 by 6 by 10. So we kind of like flip it. Okay, we're flipping the matrix, whatever it is, you know. It's like rotating it, grabbing the thing. It's, you know, something that's 2 by 3, it becomes 3 by 2. We just kind of rotate the whole thing. And that's just so that the math itself can work. All right, and then let's see. So the other part of this is that when you do the normalization, you usually also divide it by a specific term. So again, this also we will do, but let's just now perform this part. We're going to take the previous one, right, the normalized ratings matrix that we just got. Again, we're going to take the transpose of it. Again, don't worry about this part. This is just the math. You know, it's pure linear algebra on here, but we could have done this with a function. But we will take a look at this later. And then we divide it by a square root. So I'm going to do numpy dot square root of the original ratings matrix. Ratings underscore matrix dot shape 0, right? So this just means that we get the number of movies. So if I do 0 here, that would be the number of movies minus 1 because of the index. So we can always just take a look at this, for instance. If I just printed, so copy here. Let me just print this at the very bottom. Right, so all I'm doing there is I'm taking the ratings matrix, right? Which, what is the ratings matrix? It is our initial 9724 by 610. So I want that dimension, the shape, 0. Okay. I subtract 1 from it because it usually starts from 0 to something. I take the square root of that, and then I'm going to divide my previous matrix by that number. Okay, and that's usually a way to do like the scaling via math. Obviously, I don't need this anymore, so I can get rid of it. And of course, we're going to confirm down here by printing this one that that should be 9724. All right, so I'm going to run this code. Hopefully, I didn't make any errors. Okay, and then I'm going to run it. And you can see there it is, 9723, because of the minus 1. So we're just dividing. So it's simple, right? We take all the numbers in the matrix and take out the mean from them. So whatever the mean is, we take it out, normalize it, and then we just divide them also by the number of values that we have. This is a pure math-based scaling or normalization of the data. Later on, I promise we'll do an example of this with simpler numbers so that we can visualize everything. This is called, we're normalizing the data, so subtract mean and divide, let's say. Divide by 9724, which is the number of movies. And again, this should give us scale data. So now if we run it, we don't need this one anymore, right? So we have the A there, and then we're just going to plug it in. Actually, I don't think I've used X anywhere else. So really, because I've kind of in the lecture notes used the letter X, this is your X data, which corresponds to the same data as before, no labels, just data. So now that I have this, I can proceed. Let's save. Let me clear this. Run it. All right, hopefully it ran. Yep. So you can see the code works, and that's it. So that's basically it. Do you guys understand?
Yeah.
This is going to be your new homework assignment. So what you have to do, obviously, get this to run on your computer, then find another data set, not movies, right? But something else, for a recommender, like it's something that has ratings. Users to books, users to products, users to whatever it is. You'll run through this code, and then you have to make recommendations based on the parameters that you get here. Okay. Now the key issue is that we still need to do. So what information do we get from USV, right? What information do we get from that? And so that's where now I'm going to take the rest of the time just to do an example of how this works, but it's similar to what I was doing over here, right? So what I did when we looked at this matrix, I'm just going to work out an example, on the whiteboard. But as far as the code is now complete, okay? This is the code that you will need for your new homework assignment. I've already posted this on the GitHub environment, so it's already there. I provided the Jupyter notebook and also just the Python.py script. Okay, guys? So are there any questions about the code before I move on to the next part?
Are you also going to post this on Brightspace or only on GitHub?
It's only on GitHub right now. I didn't want to post this yet because we still, we're still missing the USV part, but I want to see what you guys do in the homework before we actually provide the information. You know what I mean?
Okay.
So, but this code as is right now, almost the exact same code, is on Brightspace. I think it's exactly, except for I'm sometimes like printing things. Everything is there. Okay.
Okay.
You can always just look at the video and add to that. All right. So now that we have this complete, right? This part of the code. Actually, in my code on GitHub, there's more. There are what I would call some hints. So maybe I'll say this. On the GitHub code, I have some hints. See hints on processing U, S, V. So see hints on processing USV on the GitHub code, right? There's a little bit more there that's commented out that follows after printing USV, and you can kind of think of the logic there to see if that helps you, okay? But as I said, this is an important homework because recommender systems are actually a thing that you can seriously implement in a business and you can see improvement in your revenue right away. Okay, so I definitely want you guys to do this. More so than, say, for instance, I could teach you, you know, the next topic after singular value decomposition is reinforcement learning. Okay, that one, yes, in theory, you can drive self-driving cars and things. I don't think you guys, you know, will start a self-driving car business, you know, right away, right? So it takes a lot more investment. But this one takes very little investment, and you can actually get some serious benefits right away. Make sense? All right, so that being said, we have about 13 minutes, so I think that should be enough. Code is ready. See more code on GitHub for processing. The homework is basically hopefully clear. Find a data set different from movies. Implement this, but you have to do this part. I want you to, and then you're going to ask, you know, you're going to tell me maybe to rate some things, and then after that, you're going to recommend some things for me to buy or use, and we'll see if it works or it doesn't. All right, so now that being said, this code is complete. So let's go now to the whiteboard. I just want to wrap this up with the example. I hope I have enough time. So let's do an example, kind of worked out by hand, of the same thing. So here we have an example. It's going to be about movies. Okay, so it's going to be about movies. This is going to be, you know, movies. Movies. So, and you know, let's say it's called, you know, an example. So the idea is we have a matrix, right? So we have our X matrix, X, and it's going to be user 1, user 2, user 3, user 4, you know, user 5, user 6, user 7. All right, so we have some values in here, and then of course we have the movies. So we have, you know, the Matrix. We have Alien, one of the Alien movies. We have Serenity. We have Casablanca. We have Amelie, which is some kind of, I think it's a romance or something. All right. And then we have the ratings for each movie. So you got 1, 3, 4, 5, 0, 0, 0. You can see a clear pattern there of some users like the Matrix, some didn't. Right? Then you have for Alien 1, 3, 4, 5, 1, 3, 4, 5, 2, 0, 1. Right? And then you have for the next movie, Serenity, I think it's also a type of a comedy sci-fi, 3, 4, 5, and again, a clear pattern, 0, 0. And then over here, we have Casablanca and Amelie, which are really, I think, like romance movies or historical movies. And you can see they are 0, 0, 0, 0, 0, 0, 0, 0, 4, 4, 5522. So you can almost see the grouping already, right? Users 5, 6, and 7 don't really like sci-fi, but they like more like romantic or other. Whereas the users that really like sci-fi, you can almost see them here, right? You know, like that. User 1 actually doesn't seem to like anything. So this is important because we can see this in the pattern already because we're smart humans, but the algorithm needs to pick this up. There's clearly two patterns here. There's clearly this one, and there's clearly this one. Right? You can see that there in the data. Singular value decomposition then would come in and it'll build the U matrix, right? So the U matrix here in this example would be users to what are called we've been calling singular components, but basically you can call it concepts, right? The idea that sci-fi, etc. And this would be of the same size, but obviously not all columns have importance, right? So really, this is concepts. And if you think about it, this is like singular 1, singular 2, singular 3, or maybe I can use concept 1, concept 2, concept 3, ... concept. From what we saw, it was 610. And this is also 610, right? So that's basically what we're getting here. And then we get some values, right, in this concept. So in this concept, we can see that we have 0.13, 0.41, 0.55, 0.68, and then we have 0.15, 0.07, 0.07. You see that? Here we have 0.02, 0.07, 0.09, 0.11, and then we have on this spectrum 0.59. They're opposite, but they're pretty high, right? 73 minus 0.29. And then over here on the third one, let's say we have minus 0.01, minus 0.03, minus 0.04, minus 0.05. Then we have 0.65 here, minus 0.67, 0.32. So this is a good example because it shows that, what does it show? And then I'll do ... here because I'm missing something. So there's a clear indication here, right? You guys see that? Very clear. What would you say about this? You see this clear, this here, right? And then this is another group. Do you guys see that?
Yeah.
So this kind of correlates to this one, right? So maybe this concept, even though we didn't design it to be sci-fi, it becomes sci-fi. Because there's a clear pattern. All 4 users that rated the Matrix, Alien, and Serenity, which are type of sci-fi movies, they liked. And that correlated to this concept. Really high values there, whereas these are pretty low, right? This one, I know it's kind of an odd man out, but just to keep it simple. Now, on the other spectrum, if I grab another color, let's say light green, now look at this one. This one has a clear pattern also. These are all 0, 0, 0, close to 0, positive. Whereas these are all negative, but they're pretty high, 30, 73, 59. So this has a clear pattern to this one, right? To these 2 movies. So Casablanca and Amelie, by these users, were correlated. So users 5, 6, and 7, which are these, user 5, user 6, user 7, have a very low correlation here in the sci-fi, right? You see their values or not? Like this one, this user and this one, right? They're 0, 7 in the sci-fi, whereas the other users are 55, 68, 11, 13. They're a little bit higher. So you could say that for sure, this user likes sci-fi more than this one. Make sense? Now, on the other end, you have this one, right? Where you have these are close to 0, so they don't really, they don't really like this concept, whatever it is, but they do like this concept. And this kind of correlates really well with these, right? So you're saying, well, I don't know much about these users, but I know that users 5, 6, and 7 fall in concept 2. Let's call it romance, but it could be something else, right? Concept 2, this is concept 1. So I know these.
Question.
Yeah, go ahead.
So the negative number doesn't equate to like a strong dislike. It's just saying it's a strong number.
Yeah, exactly. So you'll have to play with the data, but it's not like that in this. They just have something in common in that category, whatever that feeling is. You know what I mean?
Yeah, kind of. Like you said, I have to like mess with the data some more to see if I can understand it.
This is why I have not given you this part, right? I really want you guys to make sense of the data. But what's important here, though, is that users, if you think about it, C2, right? Users, you have to look at like the highest rank. So users, let me change colors. So for C2, users 5, 6, and 7 kind of fit in that, right? And then column 1, users, let's say for sure 3 and 4 have something in common in that category. You see that? And so now, based on that, you now have a relationship where you can say, well, user 3 and user 4 have something in common. Therefore, whatever movies user 3 rank high, I can recommend to user 4 if they haven't seen it. Or something along those lines, because you could always have a lot of users, and then you look at the movie that all the users that in that category have looked at that user 4 hasn't looked at, and that gives it even stronger evidence, right? Okay, I'm going to recommend that one to this user. Do you see that?
Yeah, no, that makes sense.
Yeah. So that's kind of how you have to interpret this data, okay? But probably for users, users didn't like this concept, right? So then those users 1, 2, 3, you kind of have to look at the movies again and figure out what they like. Now, the S matrix, I'll do it up here. That S matrix vector that you get is just really, as I showed already, the value. So 12.4, 9.5, 9.5, 1.3. What does that say? That the system is mostly sure about this one. So if you're going to recommend, start with this column. Now 9.5 is solid too, so you can probably rely on that one. However, look at this one. It's only 1.3, so maybe this column might not be very useful for your recommendations. And what that means is, there's actually no, you can't even really group the users here that well, right? Maybe 6, 5, and 32, and see what, some weird movies that user 5 likes, maybe user 7 will like them too. But that's not very clear. That's what the S matrix is telling you. Okay? All right, and then the other one that is of interest would be the last matrix, which would be the V, and the V gives you kind of the opposite, right? The V gives you concepts, but in relation now to the movies, not to the users. That's why this one was 9,724 by 9,724. Okay, because it's finding that relationship between the movies, but it's the same thing. So now it's going to say, well, these are the movies, Matrix. Let me move this. Let's say we have something like this. This is V. So these are the movies: Matrix, Alien, Serenity, Casablanca, and this Amelie, the foreign movie. All right, so then what do you have here? You have the three concepts: concept 1, concept 2, ... all the way to concept 9,724, and sort of the same thing: 0.56, 0.59, 0.56. Now notice Casablanca 0.9, and Amelie is 0.09. Then you have 0.12, minus 0.02, 0.12, and then notice these negative 69, 69, and then here this one 0.4 minus 0.8, 0.4 again. You can see there's a little bit less certainty on this one. So again, if you look at this, if I change colors here, there's a clear pattern, right? So what does that mean? Maybe concept 1, again, sci-fi. You see that? And maybe this one, again, clear pattern here. These are negative 69. These are different. So maybe romance or whatever that category would be. You don't know. That's the thing. Remember, I used the sci-fi romance thing just to kind of give you better intuition about it, but it doesn't necessarily mean that. It just means there was a relationship there, right? And that's why you look at those components. This one, again, kind of all over the place, so probably less useful, but it could be useful. At the end of the day, I'm sure Netflix and those companies, you know, they look at all their data because what they want to do is make money. So they'll try as much as they can. All right, so I've talked about that. We talked about the strength of each concept, that it's sorted in decreasing order. You guys saw that in the code. So then, you know, to kind of summarize then, the singular value decomposition then would be something, you know, now just without numbers. So we have our X matrix. So we'll be done in a few minutes, guys. So this would be users to movies, right? And then this would give us something like users to concepts. And this is going to be the U matrix. Then we have this one, the vector S that we got in the code, strength of each, let's call it strength of each concept. Strength of each concept, right? And then the V matrix over here would be concepts to movies. So as we saw before, so here we map the matrices to these concepts. And hopefully it would discover things like sci-fi, romance, but it could also discover Will Ferrell or you know, something else. Movies about hurricanes. I don't know. You know, you just don't know. But that's the beauty of it, that it can actually discover interesting things. Okay. So that's the intuition of it. So you could, the interpretation of it would be to say, you know, if you look at this one, right, and if C1 is sci-fi, then you could say, well, users, the first users, these users here, are very strong for sci-fi and very weak for non-sci-fi, that or weaker, let's say. And then if you look at this, you would say, well, the strength of the concept sci-fi is basically, you know, the SVD is more sure about that relationship. right? Whereas for the last one, it's not very sure. It's not very confident in what it discovered. So that's why it gave it a 1.3. Now, on the other end, when we look at the V matrix, V, we say the same thing. These movies, The Matrix, Alien, Serenity, are stronger for the concept C1. So these movies heavily correspond to the sci-fi concept. Whereas Casablanca and Emily don't, but they do correspond in another way, in another type of behavior with the romance category or whatever C2 is discovered to be. And that's it. That is actually, I think, hopefully clear enough. That is the interpretation of singular value decomposition. Any questions, guys? Nope. All right, so that basically concludes our class for today. We are now done with the code of recommender systems, that the homework assignment is assigned, and we've gone over the intuition. Next Monday, I will go over basically some of the more theoretical framework, and also we'll use that to kind of motivate compression, right? Which is the other application of singular value decomposition, but you can already see where I'm going with this. So if I look, for instance, at the data before, right? What am I saying? I'm saying before I represented each sample user as a matrix of 9,724 movies. However, I can decompose that into just a few concepts, right? Because you don't have to say, you know, Alien, Serenity, The Matrix, etc. as features, you know, to predict something. You could just say, these three, Matrix, Alien, and Serenity, are combined into one single feature called sci-fi. So basically, that's what we're doing, is that we're going to take, you know, whereas before we needed maybe 200 features for sci-fi movies to represent row one, now all of those really are just sci-fi. So we could definitely capture a lot of data about that just by looking at this as a feature. And so therefore, instead of ending up with all those features, we end up with fewer features. So we'll talk about that next week, but hopefully that kind of made sense where I'm going with that. But I'll again, we'll come back to this idea, and we will just elaborate how singular value decomposition can be used for compression, and in particular, how then we can use that in a supervised learning approach when we have labels. Okay? Anyway, so that will be next week. So that concludes our lecture for today. All right, so I'll see you guys on Monday. Have a good weekend.